Hello and welcome to our lab on centripetal acceleration and centripetal force. In this lab we're going to have a ball on a string. This is a sort of a simple pendulum, and I can make it travel around this preset circle. Now this circle is drawn here on the table. The ball is sort of centered above it, hanging down, and as it goes around in a circle, it does so because there is at all times a force directed inward toward the center of the circle. No matter where the ball is, the force is directed toward the circle's center. This force is called a centripetal force, and it causes the ball to have a centripetal acceleration. Now the ball's speed is not changing. It's traveling at a constant speed all the way around here. However, because its direction is constantly changing, and direction is an important part of our velocity vector. All right, so the magnitude of our velocity, the speed is not changing, but the direction is. And therefore, since the direction is changing at a constant rate, we have a constant acceleration. And that acceleration is called the centripetal acceleration. All right, here's the diagram of our apparatus. The ball is attached by a string to a pivot point, and it's in motion around the circle. The center of the ball is pulled out, and so that the ball is centered, the center of mass is right above the edge of the circle. Now as it moves around, it does so because there's some sort of centripetal force that we'll define in just a few minutes. And to start that, let's take a look at some of the forces that are acting on that ball. This is a snapshot frozen in time. It's actually in motion. And so let's sort of draw that out. Here is the ball. And first of all, there's the force of gravity. The weight of the ball, mg. So if you knew what the mass of the ball was, you could compute that gravitational force. Now the ball is moving in a horizontal plane. That means it's not moving downward. It's not moving upward. So this downward force must be balanced by an upward force that is equal in magnitude. And let me sort of draw that in as a dashed line. So we have an upward force equal in magnitude to the weight of the ball. Well, the question is, where does that force come from? The only other force acting directly on the ball is the force of tension. So the tension in the string, therefore, let me draw a dashed line over to that. Here's the tension in the string. The tension is up this direction. It makes some angle with the vertical, theta, we'll call it theta. And that vertical force that's equal in magnitude to the gravitational force is actually the vertical component of the tension. So the tension has a vertical component that's equal to gravity. And now tension also has a horizontal component. If we were to break these down into their vector components, horizontal and vertical, and that horizontal component is the centripetal force. So the centripetal force is just the let me call it force centripetal. It's just the horizontal component of the tension vector. So now we have this triangle drawn. Centripetal force is the horizontal. mg is the magnitude of the vertical. And so if you know what mg is, you know what theta is, you can determine the centripetal force. Now, determining theta is not the easiest thing to do as it's going around the circle. We're not giving you a protractor. But you should recognize that this angle theta, okay, here it is, theta, is the same as this inside angle theta. And so if you can determine that, then you can finish solving this problem. So the way to determine theta, first of all, you have to know two sides of a right triangle in order to determine the angle. So one side here is just the radius of the circle. That's something you can measure with your meter stick, the radius of that circle. The other side is the length of the pendulum. So imagine a length from the center of mass of the pendulum up to the pivot point, that's L. L is the length of the pendulum. So knowing L, knowing R, okay, it's very difficult to measure height because you don't really know how high this ball is off the compared to the pivot point. So if you know L and know R, you can calculate theta. Now you've got theta for this equation, and knowing the mass of the ball, you should be able to calculate the centripetal force. That's what we're doing in activity 1. Now in activity 2, we're going to determine that centripetal force a little more directly. You see, in this diagram, it's in motion, it's going around. There is a net force, which is the horizontal component of the tension that's directed inward. That's our centripetal force. But what if I really did want to stop the ball and hold it there? Well, in order to keep it from moving, all my forces have to be balanced. In other words, there would have to be another force this direction, which is equal in magnitude to the centripetal force in order to hold the ball there. Well, we are going to actually provide this force using a force sensor attached to the computer. And the reading of that force sensor, that force displayed, should be equal in magnitude to the centripetal force. And so the way you'll do that, it's a little bit tricky, but you can pull this ball to the edge of the circle. And I have a force sensor here. What I've done is sort of tied a string to it. And now you can take that and sort of tape it so that the string is at the center of mass of the ball. And then when I pull this out, I can pull the ball out until the center of mass of the ball is at the right above the radius of the circle. And now the force sensor should read in magnitude equal to the centripetal force. I'm kind of shaky with it. It's hard for me to hold it still. I have to hold it there for a long time while data is collecting, and it's sort of all over the place. But then what I can do is take the average using the analyze menu, the statistics function, take the average of that force over a long period of time, and that gives me a better representation of what my centripetal force is. For our final activity, we're actually going to put this in motion at last. And so I need to hold it out at the radius of the circle and give it a little push. Now it's going around the circle. And so centripetal acceleration is velocity squared divided by r, the radius. Radius is something we can measure with the meter stick, and the velocity is something we can determine, because the velocity is a distance divided by a time. Now the distance that it's traveling, one way to look at that is around a circle. So the circle has a circumference. So, and then there's also, this is a periodic motion here around the circle. If we knew how long it took to go around the circle, that would be the period or the time of one revolution. Then all we have to do is divide the distance by time, or the circumference by the period, and we'll have our velocity. So I can do that with a stopwatch. So I'll start my stopwatch, 2, and I'll measure the time it takes it to go around, maybe 10, maybe 50 times. And then I'll know a distance it's traveled, because I know what the circumference is, and I know the time it took, so I calculate a velocity. Now I just can easily find the centripetal acceleration, which is v squared over r, and the centripetal force is just mass times acceleration, so m times v squared over r, and that value of centripetal force should be comparable to the values that I determined in part 1 and part 2 of these activities.